So what we are discussing is about the probabilistic model, in which we are discussing about this hidden Markov model. It is basically hidden Markov model is a sequential model. This is a sequential model. Right? So we are considering a model like this. Say, for example, if I have three vectors getting generated with the hidden Markov model, then we have three latent variables, Z1, Z2, Z3. Z1 generates X1, the actual vector, and there is a transition from Z1 to Z2, and then Z2 is responsible for generating X2, and then Z2, there is a transition from Z2 to Z3, and then X3 is getting generated from Z3. So this latent variable basically is a vector with only one element in that vector is going to be 1 and all other values are going to be 0. Right? Suppose that if I have only two states, if we are considering that all these vectors are getting generated with two states, then each latent variable is actually represented with two elements. Say, for example, if Z3 takes the value 1, 0 means it is the first state, right? So if it takes the value 0, 1, that indicate that it is the second state, right? So we have two states in it, right? So suppose that if we have three states, then we'll get the possible values are 1, 0, 0, 0, 1, 0, and 0, 0, 1, right? So it is like that, right? Now, what is the requirement? Our requirement is to find out the hidden parameters that models this. So what are all the parameters involved in it? So particular state, right? You are in some state. What is that probability that the vector x1 is generated from that? X1 could generate from either from where? State 1 or state 2. That means Z1 can take the value 1, 0 or 0, 1. Z2 can also take 1, 0 or 0, 1. Right? So it is like that. This also takes 1, 0 or 0, 1. This also takes the value as 1, 0 or 0, 1. And Z3 can also take the value 1, 0 or 0, 1. Right? So now, being in a particular state, right? So what is the probability that x1 is getting generated? Because the vector, the arbitrary vector x1 is actually, there is a possibility that it can get generated from both the states. But the thing is, we have different probability, right? So that is normal distributed, right? So if it is a state 1, the probability that x1 is getting generated is actually described by the Gaussian density function. It is normal distributed. Right? So if this probability of x1, right? So the probability that x1 getting generated from the state 1 depends upon the parameter mu1 and the covariance matrix sigma 1. They are all the parameters, right? So similarly, if it is at second state, suppose that if it is getting generated with state 2, then you have the other parameter like mu2 and sigma 2. They are all the covariance matrix, right? Sigma 2 is the covariance matrix and mu2 is the mean vector for the state 2. In this example, we are considering only two states. So these are all the unknown parameters. And what else? I mean, these are all the unknown parameters actually. So we can list out the unknown parameters actually, right? So one is mu1, sigma 1, mu2, sigma 2. In this case, all are related with the state. The subscript indicate that it is a state. Transition probability A11. What is the probability that the state is changing from 1 to 1, being in the same state? That is the meaning of it. The probability that the state is changing from 1 to 2, that is A12. And then we have changing from 2 to 1. So that is A2. Being in the same state, that is in the second, right, state, right? So these are the unknown parameters that is actually small, right? So given a data, what is given to you is a set of data, right? The sequence data is actually given to you, right? Using that data, you are supposed to actually obtain these unknown parameters. That is the first task. Once you know this, you are comfortable in using HMM for classification, which we discussed in that first lecture of HMM. You might be knowing that. So now, to do this for maximizing, to get this unknown parameter, we are actually formulating the objective function. This is the objective function. This is the objective function here, right? So here you see that this probability is what we call it as this generating probability, right? So, I mean, I refer to this as a generating probability because this is what actually is getting generated. X1, X2, X3, and then Z1, Z2, Z3, given theta. Theta in this indicate that the parameters of this hidden Markov model, right? Given a data, this is what I'm calling it as a theta here, right? So mu1, sigma 1, mu2, sigma 2, A11, A12, everything, right, together, right? So we call this as, right, the elements of the theta in that, right? Combined together, we call this as a theta here. So given this theta, what is the probability that this X1, X2, X3, Z1, Z2, Z3 is getting generated? So that is what it is doing, right? But we wanted to maximize this one in average sense, means averaging over all possible states, right? Actually doing that, we are taking this average, right? Before that, what we are doing here is we are taking that, instead of taking the average for this probability, we are going to take average of this for computational, simplicity, right? Because when I take logarithm, the product and all becomes summation and the computation becomes simple, right? So we are introducing this ln because it's an increasing function. We wanted this to get maximized in the average sense. So we are taking this logarithm and then we are taking that maximization in the average sense. So here, this is that Z indicate that you are doing expectation over Z. Of course, remember that expectation over Z given X, right? So that is very important, even though here it is given Z in this summation. So this is about this conditional expectation, right? So we are actually computing that expectation in this, right? So we formulated this objective function. These things we already discussed. I'm just recollecting whatever we discussed in the previous class, right? So this is the objective function which you would like to maximize. This is the goal. This is the thing, right? And what we did was we represented this P of X comma Z, right? Using the expanded version, right? So you may just recollect quickly what is that we did. Of course, we have X1, X2, X3, Z1, Z2, Z3. It means that we have that initial probability, right? Pi 1. In fact, it is going to be that probability that the first element X1 is getting generated with any one of the state, right? Let us say that if the first element is getting generated with that state 1, right? So then it is pi 1. Then we have a, right, or otherwise it is more general, right? Because we are having this Z1 in this. Probability of Z1 is going to be the probability that X1 is getting generated from that Z1, right? Z1 take either state 1 or state 2. So it depends upon the value of Z1, it will take either the value pi1 or pi2, right? So suppose that if Z1 is 1, 0, right, it gets the value pi1. If it takes the value 0, 1, then the value is going to be pi2, right? So this is the first step. And then being in a state Z1, right? So it's a latent variable, right? So X1 is getting generated with given Z1, right? So that is what is needed in that independent event. And there is a need of transition from Z1 to Z2. And then X2 is getting generated with what? Z2. And then we have the transition from Z2 to Z3. And then finally, X3 is getting generated with Z3, right? So this is what the probability is, right? So we tried representing this one in a way. That's what that lecture 2 of HMM gives you that information, right? So after replacing the corresponding value for P of Z1, P of X1 given Z1 and so on, we get a modified expression. That derivation is what actually we discussed in that lecture 2. I'm not going to give the complete details on that. I'm just giving only the outline, right? So from this to this, how we get, right? So that is the lecture 2 of HMM. You can see through that lecture. We discussed in detail this one, right? Now, so this is what our requirement, this is what actually you wanted to maximize, right? But we are able to represent this one in this form. So from this to this, actually we have a flow, right? So how we actually got this, it is known to you. And let me explain what are the parameters in this expression, right? So what are the things, right? So we have the prior, the probability of that first one, right? X1 is getting generated, right? In which state? So that is what is that pi k here. And we have a transition probability here, AJK, and this is the actual generating probability, right? X1, Xn getting generated with, right, the kth state, right? Phi of Xn given phi k. It means that Xn is getting generated with the kth state, which is actually described by the Gaussian density function, right? Which is actually described by the parameters like mu k and sigma k, the mean vector and covariance matrix that is actually occupied in this, right? Apart from that, we have now additional parameter like gamma of Z1k is at n minus 1j is at nk, right? So what is this, right? So this is basically that probability, right? As you see here, gamma of Z and k is actually expectation of Z and k, but it is basically because this Z and k takes either the value 1 or 0. Here we have 2 subscript. Whenever you see 2 subscript below this Z, it means that element of this Z, right? So because you know the latent variable Z having the values like 1, 0 or 0, 1 in case of 2 state, right? So these are the, right? So this, whenever I'm having 2 subscript in it, Z and K, if it is a Z and K like this, right? So then it means that the element of the latent variable, right? So what is that N and K indicate? N is basically the nth sample getting generated from that model. It is otherwise nth latent variable. That is what, right? But this K indicate that is the element, right? We have that K is at 1, 1, is at 1, 2, like that. Is a K actually indicate that state, right? So if I have that K as this one is at n1, Zn2. It means that this is basically the value. Suppose that if the value here is 1, right, N1 is taking that value 1, indicate that it is getting generated state. If it is 0 and 1, then it is getting generated with the second state. It is like that, right? So Z, in a short, what I'm trying to say here is Z and K actually 0, right? So when I have a expectation over the random variable, if I have a expectation over the random, and if that random variable takes either 1 or 0, right? So then how to do that? It is basically 1 into probability of x is equal to 1 plus 0 into probability of x equal to 0, right? So this will get cancelled. It means that it is just, if I take expectation and if the random variable takes either 1 or 0, right, the expectation of that one, that will give directly the probability itself. That is the reason what I am going to tell now is of Z and K is the conditional probability. Of course, I told everything is taken the expectation given X. We say this gamma of Z and K. Gamma of Z and K. This is another way of writing this. Gamma of Z and K can be written like this, right? So it is like that. Z and K equal to 1. So it is like that. Suppose that if I write it as a gamma of Zn, right? So it indicate that. So because Zn takes any one of the values 1 or 0, right? Any one of the values 1, right? So in that case, we are actually talking about the element that is actually 1 in this case, gamma of Zn. In short, we'll write like this: probability of Zn equal to 1 given X, right? So whenever I'm having a single subscript, right, I'm talking about this, the vector, right? So having the two elements in it. And the double subscript means it is a specific value of it. I mean, the kth state. That is what it is giving you. So Z and K in this case, this K indicate that state information is also given in this. So, but here when I say that Zn, so the state information, because Zn can take or 0, 1, so indirectly the state information is available. So in short, we can actually write it as gamma of Zn, which is probability of Zn equal to 1 given X, right? So of course, now, as of now, we are writing with the double subscript gamma of Z and K. Why I'm telling this one is these are the additional variables getting introduced while doing this job, right? While simplifying this expression here, get introduced with another two variable called gamma and zeta here. So what is this? This is exactly like a transition probability, but it's not it is not the transition probability, right? So it looks like that. I mean, here the nth element is getting generated with the kth state, and n minus 1th element is getting generated with what? Jth state. This is a joint probability. This is the joint probability, whereas your AJK is basically the conditional probability. That is the major difference. This is the conditional probability, but describes the same thing. Of, right, Znk given Zn minus 1 J. That is the meaning of it. When the moment when I write AJK, it means that probability of Znk given Zn minus 1 J. It means that n minus 1th element is getting generated with what? The jth state. And nth element is getting generated with what? The kth state. But here it is a conditional probability. But when it comes to that zeta, which actually gives you, we are writing this one as the expectation here. The same argument as the elements takes either the value 1 or 0, right? The expectation actually gives you the probability itself. This expectation gives you the probability itself. Z n minus 1 j equal to 1. Z, I mean, Z, let me write, Z nk equal to 1 given x. Right? So this is what this probability I'm talking about. That is a joint probability, of course, condition on x. That is what theta indicate, right? So you have to able to now understand the new parameters introduced in it, right? So the new parameters are, and this is what the meaning of it. Z on k, that is nothing but probability of Z on k equal to 1 given x. So that is gamma of Z on k. In more general, gamma of Z n k is the probability of Z n k equal to 1 given x, like that. Okay. Right? Are you able to hear now? Yes. Okay, fine. Right. So now you got this expression q in a modified form, right? So that is what I want to say. Right. So what we actually achieved, this q now in terms of gamma and zeta here. So we are going to use this one for, right, the to maximize, right? So this one you are going to maximize such that, you know, I mean, the value of the unknown parameters like pi k and then ajk, and then this one is basically mu k, sigma k. This together, I mean, whatever I have listed now. So this is what we call it as theta. Of k and ajk for all values of j and k's, and then mu k all values of k's, and then sigma k for all values of k, right? So all values of k means depends upon the number of state. Suppose if I have 2 state, you get k equal to 1 and 2, right? So this is what this thing is, and we are interested only on this. This is what actually our requirement is, but we got the other parameters introduced here. Right? So now to attack this problem, we are actually going for what is called expectation maximization algorithm. In short, we call this as an EM algorithm, expectation maximization algorithm. Right? So now what we have to do is we are actually getting the expression for pi k, ajk, and of course mu k, sigma k, everything, right? In terms of gamma and zeta, in terms of this gamma and zeta, which in further need the value of pi k, sigma k, all those things, right? I repeat, gamma and zeta requires the theta. I mean, theta means now you know what it is, right? This needs that. But for computing the parameters of theta, right, we need this gamma and zeta, right? So now what we are going to do is we are going to initialize the value of theta called theta old. We have some value is theta. It means that you are initializing that value as some value. I'll tell you how to initialize and all maybe after this talk, but let us assume that you are initializing these values, right? So you have this sigma k, mu k, all those things are initialized, right? Then you are going to, right, get the value of this gamma and zeta, right, which we call it as, right, the expected value of this gamma and zeta, which we call it as the expectation stage, right? Once you know this gamma and zeta, you are trying to maximize this, keeping this is known, keeping this is known. These are known, right? Known, right? So you get a expression for pi k, mu k, sigma k, all those things, in terms of gamma and zeta, right? Of course, with the constraint. What is that constraint? You know that constraint that sigma, I mean, if I have this pi k getting summed over all the state, right? So suppose that if I have capital K is the number of states, if I sum together all those things, that should end up with 1. This is the constraint. And we have another constraint here, which we call it as this AJK. It means that, as I told you, there is a change over from where? N minus 1 in the jth state to the kth state. When you are in the jth state, you have only k choice, right? For moving from the jth state to first state, you can go, or jth state to second state, you can go, jth to third, and so on. So when I do this summation, this will also end up with 1, right? So using this constraint also taken to account, if I do this maximization means the moment when I try to get that value of pi k, that it maximizes this, right? In this case, what is happening here? That second term and the third term is not playing any role because we are interested in maximizing pi k. Of course, the constraint will come into play here, right? So we have to introduce that constraint also, and using this Lagrange, right, technique, and then doing this differentiating with respect to pi k, you get an expression for pi k. And this is what we call it as expectation stage. What you see here is the result for that. You see that this is what I'm talking about. This is what we call it as this maximization state. It's very important, interesting. I'm not giving you that complete steps involved in it, right? By doing differentiating on that, and if I equate that to 0, right? And with the having what applying the condition also, we get an expression for pi k in terms of gamma. You see that. And similarly, AJK in terms of that zeta here. And then mu k, as I told you, that mean and covariance matrix, right? So that is also in terms of gamma here, right? But you see, what is more interesting here is for computing, for example, let us say that, this gamma and zeta, right, that demands this parameter, that needs a model, that needs the model to get it, right? Because after all, what is its gamma? Gamma is basically the probability of Z1k equal to 1 given x. To do this computation, which we need the model, means which demands your pi k, AJK, mu k, and sigma k. And that's what we have two stages in it, right? One is the expectation stage. The another one is the maximization stage. This is the expectation and this is the maximization stage. In case of this expectation, you are going to have some expected value of gamma and zeta, right? And then when it comes to this maximization, which gives you the value of pi k, AJK, mu k, and sigma k, right? So it is like in a loop, right? You are initializing value of, right? I mean, expected value of this gamma and zeta you are getting. Using that, you are going to maximize that function so that you get this parameter. This parameter is helpful in updating the expected value of this gamma and zeta. So this is being in the loop. This is in the loop. This is expectation and this is the maximization. This is in the loop. After some iteration, you feel that your probability, whatever we had, that Q value is not actually changing much. It is actually reached the maximum. As the iteration goes, right? So your Q value is going to get increased. After some time, it is saturating, right? You can stop at the is where this Q value is not changing much, right? So that place you have to stop. After that, we are actually interested. We are interested on these parameters, which is basically the model of the, right, the sequential model, what we are talking about, hidden Markov model. For that, these are all the parameters. These are all the hidden parameters. So these parameters, once you get, then your model is ready. Your model is ready only if I know this value, right? So this is the intermediate step, right? Gamma and zeta, we get that, right? But getting this gamma and zeta is again a challenging, right? So we know what is that maximization stage now. Maximization stage is this, which is there in this slide. It is very clear now. Now we are interested in going for this expectation stage in detail, where we have to get this value of this gamma and zeta, right? So I repeat, this is the expectation stage, and this is what we call it as pi k, aj k, mu k, sigma k. This is the maximization, expectation, maximization, which is in the loop, which we call this as the expectation maximization algorithm, right? So now we will quickly see to how to find out this gamma and zeta. Just a moment, I will take another slide. Okay, right. So now coming to this expectation maximization algorithm. Now you know the notations will go a little faster, right? So this is very simple only, right? So in that expectation stage, we get this gamma and zeta, and then maximization stage, we get this mu k, sigma k, pi k, and akl. Now you know that what it is, right? So we discussed and we got an expression for maximization stage. We are interested about this expectation, right? As I told you, what is this gamma? Gamma of Z and K is basically the probability of Z and K equal to 1 given X. So using Bayes, you are writing probability of Z and K equal to 1 comma X whole divided by probability of X, and then doing the other way around, right? So it is just a Bayes expression what I'm writing here. So probability of X given Z and K equal to 1, right, into probability of Z and K equal to 1, the whole divided by what? Probability of X, right? So now this expression, right? So this expression, to get this expression, we are introducing additionally another two parameter, which we call it as alpha and beta, right? It means that this is over, right? Your expectation and maximization is in the loop. That is fine. And now to get this gamma and zeta, we are introducing another two parameter called alpha and beta. I tell you what is that. This alpha and beta is helping to get this gamma and zeta by using what we call it as forward backward algorithm, right? Prediction algorithm, forward backward prediction algorithm. Otherwise, what we call as this Baum-Welch algorithm, right? Right. So what is that about? Right. So it is a lengthy process. Actually, HMM is a lengthy process, right? So this is forward backward algorithm, basically prediction algorithm. Right. I repeat, the outline is very clear, right? So you have this gamma and zeta that gives you this mu k, sigma k, pi k, akl using this expectation maximization algorithm. And within that expectation stage itself, for getting this gamma and zeta, we are actually introducing another two variable called alpha and beta. So that actually describes this probability of X given Z and K equal to 1. How? You see that. What is alpha of Z10? Here it's here from this point onwards, we are not actually using the double subscript. We are using that single subscript, right? So indicating that Zn, right, either takes the value 10 or 01. It is like that, right? So it's basically the nth Latin variable. That's what it means, right? So alpha of Zn means probability of x1, x2, x3, and so on up to this xn, comma Zn, right? Comma Zn. It's a joint probability, which we can write probability of x1 and so on up to this xn given Zn into probability of Zn, right? Why I'm doing that? There is a reason for it. Beta of Zn is written as probability of xn plus 1. You see that it starts with n plus 1. Here, actually, we are talking about the sequence from x1, x2, and so on up to this xn. So this is the actual sequence getting generated, the sequential vectors, right, getting generated. There are capital N number of vectors, right? You are going to divide this one into two parts. One is x1, x2, and so on up to this xn. And then from xn plus 1, it starts, goes all the way up to xn here. Right? So this is the first part in this, right? So, and we have a second part here. And remember that this model generated up to this xn, right? Right? So, and this from xn plus 1 onwards, right? We can write it as a splitted form using this Latin variable. Because for getting this xn plus 1, what is important, what is needed is Zn plus 1 is response for xn plus 1, right? So we can write this one as a split form that we have to do. So I get this beta of Zn as probability of xn plus 1. The same thing here, it starts with x1 up to xn. Beta of is actually in that case your probability depends what? I mean probability of what? Xn plus 1. It starts with n plus 1 and it goes all the way up to this xn. Zn. Given Zn here. And remember the joint here, it is not given. Here. There are reasons why, because I want to write this gamma in terms of this alpha and beta. Because we know this gamma of Zn in the previous slide was probability of x given Zn into probability of Zn. Right? Now in place of here, like x1, x2, and so on to this xn. And we have to pass it up to this xn and then from xn plus 1 all the way up to, right? So this one, right? Splitted form. We are able to write it as one part is what? This probability of x1, x2, x1, xn, right? So this one, we write it as a product of two probability. One probability is the probability of x1, x2, and so on up to the xn given Zn. This is the conditional independent. This is called the conditional independent. The model what we have considered is a conditional independent fashion. The reason is what? Given Zn, whatever is getting generated, right, all the way from x1 to xn, which is having some probability, right? Given Zn, right, the probability that xn plus 1 and so on up to this xn, right? So these two probabilities are independent as far as this consider, right? So because in your model, what is actually happening? So if the about that, this is Zn, Zn is response moving to what? Zn plus 1 because we have a transition, right? But as far as this xn plus 1 is considered, it is getting generated due to this Latin variable Zn plus 1. Xn plus 1 purely depends on what? Zn plus 1. Of course, Zn plus 1 depends on Zn. That is fine, right? So given Zn, the probability that xn plus 1 all the way from xn plus 1 to xn right? So that we can separate it out. All the 10, this independent probability. They are the independent. We call this as a conditional independent. First term, and then we have when we multiply these two, we get what's called alpha, and this is the definition of beta. So you have to write this gamma. This is the interesting and very important step. Your gamma of Z10, we are able to write in terms of alpha and beta. That is the idea. So alpha of Z10 into beta of Z10 whole divided by what? Probability of X. In the same also be written in terms of this alpha and beta. Like that, the form. Because by definition, what is zeta? It is basically this probability of Znk equal to 1, Zn minus 1, L equal to 1 given X. Right? So we are writing in short this one with single subscript, as I told you, for convenient. But remember that when I say Zn, which actually takes either 10 or 01, so that will indirectly gives you the information about the state. Right? So we need not explicitly mention K and L because the value of Zn will give you the information about the state. If Zn is 10, is a state 1. If it is 01, it is a state 2. So we are actually removing this K and L. We are writing in short Zn and Zn minus 1 here. Right? So in short, again, probability of Zn, Zn minus 1 given X. That is what your zeta is. Now using this, probability of Zn, Zn minus 1, X whole divided by probability of X. Fine. Again, probability of X given Zn, Zn minus 1 into probability of Zn, Zn minus 1, right? So I hope this is clear, right? So this one is written as what? Probability of X given Zn, Zn minus 1. This is getting multiplied with what? Probability of Zn, Zn minus 1. And this X is being expanded here, like X1, X2, X3, and so on up to this Xn. It is expanded here. Now you are going to split this probability, right, from up to this n minus 1 here purposefully. In the earlier case, for getting this gamma, we split it into n, right? But here we are going to split up to n minus 1 because we have a condition over n minus 1, n as well as n minus 1, that is there. Is xn minus 1 and then xn, it goes off. We are going this one in parts rather troops up to is part and n is the second part and then plus 1 is the third part, right? So why we are writing this one? Because the one is 2 and to this xn minus 1 given and Zn minus 1, right? Even though the condition to the role minus, right? What I'm trying to say here is when I write this up to this minus 1 given Zn, Zn minus 1, if I write like that, right? In this case, the condition on Zn is not actually playing the role in generating up to what? N minus 1, right? Because with what? The latent variable is Zn minus 1 only, right? So no way Zn is playing the role. So that becomes now, even though the condition on Zn is coming in this picture, so we are going to remove that Zn and we are writing that this probability of x1, x2, x1 given Zn minus 1. And this term, xn given Zn, right? Because Zn is responsible for generating what? Xn here, right? So is considered, we are having a condition of Zn only. And similarly, for the remaining portion, n plus 1 all the way up to what? N is actually your Zn is responsible for that, right? So we are writing this one in 3 parts, and this one further we are writing in a Bayes, probability of Zn given Zn minus 1 into probability of Zn minus 1. Now we can relate this one with alpha and beta. Based on the definition of alpha and beta, right? So what we are going to do now is we are going to combine. So we are writing this zeta in this form. Now you are going to on beta, right? So that's what we are going to do, because we have alpha as the joint probability, x1, x2 up to xn, and zn it should come in this place, right? So now if I combine this one with this, you get a joint. So I can replace that one with alpha of z, right? Alpha of Zn minus 1. And this one, xn plus 1 all the way up to this xn given Zn, right? So this is like beta. So this one, we can write it as beta of Zn. So we have an expression combining these two. Combining these two ends up with alpha of Zn minus 1. Right, and this one is actually becoming beta of Zn. So what I'm doing now is I'm trying to write this whole expression in terms of this alpha and beta. So you get this x. So whatever, okay, here. Right. So that step I have not written explicitly. You can write it yourself. It's not difficult, right? So what the expression is Zn minus 1, right, into probability of xn given Zn, and then into beta probability of Zn given is. This is in the numerator part, and the denominator part you get only this probability of x. So this is the final expression for zeta, right? So this one is what actually you are getting now for this zeta. So we are writing this one in terms of what? Alpha and beta. That is the idea. So once you know this value of alpha and beta, of course, remember alpha means not just one alpha, right? Alpha of Zn minus 1 means all the values of z's you must know. Alpha of Z1, alpha of Z2, and so on, right? So now the algorithm is like this. I repeat what here. So this is what this algorithm is, right? So you are actually need this alpha of Z1, alpha of Z2, and so on up to what? Alpha of Zn, and then beta of Z1, 2, right, and so on up to this beta of Zn, and these values are directly related with your gamma and zeta discussed. Using this alpha and beta, we are able to get this gamma and zeta, eta, and then, right, using mu k sigma k kl, and using this again, we have to go for finding beta, then gamma and zeta, and then it goes to this mu k sigma k pi k kl. So this will be the maximization, expectation maximization algorithm. But how to get these alphas and betas? That is still remaining now, right? How to get these alphas and betas? And this is what you are going to get using forward backward prediction algorithm, right? So it means that you are going to have the sequence of getting these alphas, right? So what is that about? You'll see that. Able to write your alpha, right, in terms of alpha of Zn minus 1. We'll see the steps. But now I'm just saying that alpha of Z10, we are able to write Zn minus 1, right? So you, or in other words, we can say alpha of Z minus 1 is helping you to get this alpha of Z1. So this is, so if I know alpha of Z1, we can get alpha of Z2. If I know what is the value of alpha of Z2, we get the value of alpha of Z3. It goes like that, and we get this alpha of Zn. This is called this forward part, forward prediction. You are going to do this values, right? Prediction like this. And then in the same fashion, we have beta. This is the beta part. Here we have a one. You see that beta of Z10 here in this expression, this beta of Z10 is actually giving you Zn minus 1 in this, right? So it means that it starts Z10, right? So which gives you the value of beta of, right? It goes like this, and then beta of Z1. So this is called this backward prediction. So that is hence the name is actually forward backward prediction algorithm. You have these alphas for this forward prediction and beta prediction here. We are alpha of Z10 into the steps are very simple. You can see that the steps, you know, by definition, alpha of Zn, that is probability of what? A definition. So you are using that, right? And taking the summation over Zn minus 1 is basically the marginal probability. I hope this is known to you. What I'm written is what? And take the summation over B, you get a marginal probability of, right? So this is true for two variable. For example, probability of AB, if I want to know, I can introduce a new variable called C, and then if I take values of C, get this. So that trick actually using what is called sum over. That is a trick of alpha of minus 1. So the probability of, yes, we need to initialize a beta of n and alpha, right? We need to initialize beta of z and so now let's see quickly what is that sequence in this equation, right? So now xn minus 1 the picture give Zn minus 1. This further we can Zn minus 1 Zn minus 1, right? And here we are writing up to n minus 1 is one term. Xn alone is coming as the next term, right? Up to xn minus 1 and xn is coming here, right? So as you know that one Zn is not playing any role, so you are going to remove that. So you are getting this is the probability. Zn is vanishing in this, and here Zn minus 1 is vanishing. So probability of xn given Zn is coming in this picture, right? So this expression is the same, right? So the same thing is coming in this, right? Only thing is we are split it into two parts, which is called this conditional independent. Independent, that is what I'm saying. As far as this model, what we are considering, right, is a conditional independent, right? Okay, it's called this conditional independent. right? So now when you see the definition for this is going to be your alpha of Zn minus 1. This probability is coming as it is, and this probability we are able to write it as, okay, we are able to combine this to get this, right? So not this one, because as far as this alpha is considered, it is a joint probability, right? So I tell you that this one multiplied with this will give you alpha, because multiplied with these two elements, if you get it multiply, you get this probability of x1, x2, and so on up to this xn minus 1, comma Zn minus 1. It becomes a joint probability. So when you are this term 1 and this term 2 is getting multiplied, you get it as alpha. And this probability of xn given Zn is coming as it is. And this probability of Zn given Zn minus 1 is coming as it is. Right? So this is the recursing part, alpha of Zn in terms of this alpha of Zn minus 1. Right? So now let me go to that question from Shiva Shankar. Let me read it. I don't know what is this asked. Yeah. If we start with the go forward for alpha and backward for beta, then how is it possible to iterate over each step? So that is the question. We need to do as I do. Okay, I'll tell you that one here. Or right stage, we need to go for what is called this maximization stage. Okay, what I'm trying to say here is the complete set of gamma and zeta, you are going to have it, you have to compute, and that will give you, it is not just one value, you have to actually do it for all possible values of n. For all n, you have to do that. For all n, you have to do that. For all n, right? And then, because you know that mu k involves all here. So that I think that is there in that other slide. You know, difference sigma over n, right? So it means that this actually we need to compute this gamma and zeta for all values of n forever. Mu k sigma it will help you to get these alphas in the forward form, alpha of Zn, and then beta of Zn, and it goes this way, and then we are going to get this beta of Z1. And these two combine together, which is going to be helpful in getting your gamma and zeta for all values of n again. That is the important thing. Then once again, it goes to this maximization algorithm and then backward, right? For every iteration, we have this forward and then backward for every iteration. For every iteration, this is what the complete work we need to do, right? So we have to get this gamma and zeta for all values of n, and then go for this maximization, get the value of mu k, sigma k, pi k, akl, and then come back to this expectation stage. In the expectation stage, you have to get these alphas, all alphas, alpha of Z1 all the way up to this alpha of Zn, beta of Z subscript capital N up to this beta of Zn, and then that helps you to get this gamma and zeta for all values of n, and then again goes to this maximization back and forth, and finally, right, it needs to converge. Now what we are actually discussing is we are actually getting that value of alpha of Zn in terms of what? Alpha of Zn minus 1. That's what we got now, because this is the expression where this forward prediction is happening. And the same fashion, we can actually do it for the backward prediction, right? So this is the final result, and the flow is like this, what I have written at the bottom. We can quickly go through that also. So this is the starting point, beta of Zn, right? So this is probability of xn plus 1 all the way up to this xn given Zn, right? So now your beta of Zn minus 1 means it has to start with what? Xn. So let me start with beta of Zn minus 1, because this is basically, I want beta of Z n minus 1 to be written in terms of beta of Zn. It's a backward one, right? So let me start with beta of Zn minus 1. So it starts with xn, n plus 1, and so on up to the xn given zn minus 1. You have to be careful. And this is a very straightforward joint, Bayes technique, converting this probability of AB by probability of B fashion. The same trick we are going to introduce here also. What we are going to do? We are going to introduce the variable called Zn and taking the summation over Zn, right? Taking the summation over Zn, introducing Zn and taking the summation over Zn. That's the thing we are going. Again, here and then xn plus 1 all the way up to this xn, right? So the split up is like this. It starts with xn plus 1. It goes like this up to this xn. We are going to have a split up like this. Xn is one term and the remaining things is another term. And this probability is coming as it is in this. As usual, xn doesn't depend on zn minus 1. So we are removing, we are putting this probability of xn given zn. And here xn plus 1 all the way up to this xn given. Again, it doesn't depend on zn minus 1. We are writing condition on zn alone. And then probability of zn given zn minus 1. And by definition, this is coming as it is. By this one is by definition is beta of Zn. This is beta of Zn, right? Which is basically the, remember, betas are the conditional probability. Alphas are the joint probability, right? So this is beta of Zn. So this probability of xn given Zn is kept as it is. Beta of Zn here, and this probability of Zn given Zn minus 1, that is written like this. So finally, what you have to understand here is this expression beta of Zn minus 1, we are able to write in terms of beta of Zn. That is the key point, right? So this is actually responsible for backward algorithm, backward flow, right? So we have this forward and backward, and that's the final topic actually of this this HMM. I would like to summarize the HMM like this, right? So you are going to have HMM, the data are given. You are going to initialize some value for mu k, sigma k, pi k, akl, right? And usually that is initialized using k-means algorithm. We will discuss that one in the next class. K-means algorithm. And using these initialized values, you are going to compute this expected value of this gamma and zeta, which actually you are going to get by using this backward forward algorithm by introducing a variable called alpha and beta, right? So it is like that. It goes all the way up to this alpha of Zn, and then beta of Zn. It goes all the way up to this beta of Z1, which actually gives you this gamma and zeta here. So like this, right? So this is responsible for this, for getting this. And once you get this, right, you once again, you are going to go for this maximization algorithm where your mu k, sigma k, pi k, akl, everything is written in of gamma and zeta, right? So all the expressions are in terms of this. So we are able to get this value. And once again, you have to go for this expectation, then maximization, then expectation, and then maximization until that Q value is getting converged. The Q value is going to get converged in the iteration. Once the values are getting converged, you have to freeze the value of mu k, sigma k, pi k, and that is the model of your hidden Markov. And remember, we need to do this model for example, if it is a speech signal, we have to do this model for every such word. Imagine how complex it is. For every word, we are supposed to have one particular model. I mean, if you want to classify the word, if you want to classify the sentence, then we have to go for that. I use the example of classifying the digits, right? So that is the example what I took signal. So it all depends upon that, right? So if I want to classify one among this 10 digits per any person, then we need to have 10 HMM model. 10 model is for the individual digit, and if the new uh, word is coming, right, spelled one among this digit, you would like to know which digit it is, then we have to go for the generating probability of this HMM using the model created, and we have to declare that word belong to that particular digit whose generating probability is the maximum. If the HMM 1 is giving you, if 2 is giving you the maximum generating probability, then declare that it is a digit 2, right? So we are actually going to get that value of the probability for all the model whatever we have created for 10 digits, right? And we are supposed to compute this generating probability for values of this, right? The model what we had. So this may be the one, and somewhere the generating probability here it is going on something like that, and we have to see whichever is maximum in this, and then we have to declare that the 2 is the word the spelled, right? So for getting this model is what actually I am talking about. For getting this model, we are actually going for this expectation maximization algorithm. And one component which I am not going to discuss, but you can expect a question in the exam is what is the value of alpha of Z1? So this I am purposefully leaving because I want you to explore these things in detail, right? So I don't want to tell this answer explicitly, but you can expect this question in the 10th semester, right? So as I told you in that forward backward algorithm, we need this alpha of Z1, which actually gives you that of Z2, right? So that is that forward, right? So alpha of Z1 gives you alpha of Z2. It goes like that, right? So it is like that. And then beta of Z10 gives you that beta of Zn minus 1. And it goes like that and ends up with what? Beta of Z1, right? So now the question is, what is these values? Because once you get this alpha of Z1, then only you can get alpha of Z2. So what could be the value of this alpha of Z1 and beta of Zn? And here you see that it is a capital N. It is basically the length of the sequence, the vector, right? So it is like that. So this one I am not going to tell the answer, which is available, of course, in the book. You can see, but I don't want to tell you because I want you to explore that. But you can expect that question in the end semester, right? Stop here. So this is about this HMM, and what is left out is GMM and K-means algorithm, right? We will discuss that one.